The question we are solving now belongs to test series 5. It is of network theory subject. In specific, it belongs to sinusoidal steady state analysis. As per the question, there is a AC circuit given as shown in the figure. The AC circuit has a current source of 2 sine of 2t ampere, which is connected in series with a 1 ohm resistor, and this whole combination is connected in parallel with a 1 Henry inductor and a voltage source of sine of 2t volts as shown. This combination is in turn in parallel with a 0.5 farad capacitor, and the output terminals are across the 0.5 farad capacitor, which are marked as A and B. We need to find the Thevenin's equivalent of this circuit as seen from terminals A and B. We see that the circuit doesn't contain any independent sources. From this we see that the Thevenin's voltage phasor can be written as open circuit voltage phasor as seen from terminals A and B, and the Thevenin's impedance can be written as the impedance as seen from terminals A and B upon replacing each of the sources by their equivalent resistances. So for doing the same, first let us draw the equivalent circuit in the phasor form. And also please note that the circuit is operating at an angular frequency of omega 2 equal to 2 radians per second. So because of this 1 Henry ohm inductor will have an independent impedance of J2 ohms, and the voltage phasor can be replaced by 1 at a phase of 0, and the capacitor has an impedance of 1 by j omega c, which can be written as minus j. So from this we see that the open circuit voltage using the superposition theorem can be written as shown. So when the current source alone is acting, the open circuit voltage can be written as 2 at a phase of 0 multiplied by J2 divided by J2 minus 2. This quantity J2 minus J, this quantity is the current flowing through the impedance minus J. This should be multiplied by minus J to get an idea about the open circuit voltage when current source alone is acting. Now when voltage source alone is acting, the open circuit voltage can be written as 1 at a phase of 0 multiplied by minus J divided by J2 minus J. This is due to the reason that when voltage source alone is acting, current source should be replaced by open. So the open circuit voltage between terminals A and B can be found out using the voltage divider rule. So this upon simplification can be written as minus 4j minus 1, that is equal to minus 1 minus 4j volts. Similarly, the Thevenin's impedance as seen from the terminals A and B can be written as shown. For this, we replace the current source by open and the voltage source by short. So we will be left with only the parallel combination of J2 and minus J. So this can be simplified as J2 multiplied by minus J divided by J2 minus J, that is equal to minus 2J ohms. So from this we see that Thevenin's equivalent circuit will have a voltage of minus 1 minus 4j volts, and it has an impedance of minus 2j ohms. Now upon converting the same to the time domain form, we see that VTH of t can be written as root 17 multiplied by sine of 2t plus pi plus tan inverse 4, where root 17 is the magnitude of minus 1 minus 4j and pi plus tan inverse 4 is the phase of the same, and we have put 2t here because the circuit is operating at 2 radians per second. Similarly, the Thevenin's impedance can be written as minus 2j ohms. So from this we see that the Thevenin's equivalent circuit will have the Thevenin's voltage as marked and Thevenin's impedance is as marked. From this we see that the correct option representing the Thevenin's equivalent circuit as seen from terminals A and B is C.